Hi everyone, and thanks to the organizers for inviting me to give this talk. My name is Bob West and I'm an assistant professor of computer science at EPFL in Switzerland. What I'm about to present is work in progress that we're doing in the context of the Microsoft Turing Academic Program. Most of the credit here goes to my postdoc Maxime Perard, who is leading this project, and also to my PhD student Martin Józsefowski, as well as to our fantastic team of collaborators from Microsoft Research and Turing. The starting point for this work is the observation that machine learning algorithms tend to pick up on spurious correlations. That is, correlations that don't reflect causal relationships in the world. Let me use an example that has been popular in the previous literature and that nicely relates to where I live, Switzerland. Imagine that you want to train a machine learning algorithm to detect cows in images. A large fraction of cow images on the internet were taken in alpine settings. So in many cow images, we'll have grass on the ground, snow-covered mountains in the back, etc. This can lead the machine learning algorithms to rely on such features in order to decide whether there's a cow in the image. But cows, of course, exist in many other settings as well. For example, in the Mediterranean environment of Corsica. There's no Swiss-style setting here with grass and mountains, so algorithms trained on typical data sets of cows won't find the features that the algorithm has learned to rely on, and it will fail to recognize many cow images as such. So in a nutshell, the problem is that causation doesn't equal correlation. While I use the task of image classification to motivate the problem, our project actually focuses on the task of language modeling. Here the input is word sequences rather than pixel maps, but the same problems arise. How can we fix these problems? Recent work has focused on two broad approaches: bias mitigation on the one hand, and causal inference and reasoning on the other hand. The bias mitigation-based approach is bottom-up. Here one starts by observing a specific spurious correlation, such as gender bias, for example, and then adds a penalty to the loss function in order to steer the model away from paying attention to those spurious correlations. The causal inference-based approach, on the other hand, is top-down. Here one starts from a causal graph of the model situation, and then one identifies spurious correlations as those correlations that don't correspond to the causal paths in the graph. Both of these approaches have certain shortcomings. Bias mitigation can be a tedious, never-ending process that doesn't scale up easily. Usually, whenever you remove one type of spurious correlation, others pop in. It's like a hydra. You chop off one of its heads, and it grows two more. Moreover, some forms of spurious correlation can be inherently hard to detect and measure. We might not even know there is a spurious correlation in the first place. Causal inference-based approaches, on the other side, also have major problems. For example, writing down a causal graph is notoriously hard. Sometimes it's not even clear at all how to begin to think of a causal model for a given domain in the first place. And language modeling, our task, is precisely of this nature. Typical language is constrained by causal relationships in the world. For example, when I tell my daughter to not press the escape key while I work because it will make me lose all my unsaved work, she only understands this because somewhere in her head she has a causal model that specifies that a key press has consequences inside a computer, that the computer also stores the work I do, and so on. Current language models don't encompass such causal models, but are exclusively based on word co-occurrences and are thus vulnerable to spurious correlations. A rigorous causal inference-based approach to removing spurious correlations would require us to first model all those causal relationships in the world, an impossibly difficult task. It is not even clear what should be the variables in such a causal model in the first place, let alone the causal links. In order to build up our approach toward removing spurious correlations from language models, let me retrace some of the recent advances in causal machine learning. One key observation, called invariance across environments and first rigorously made by Peters et al. In 2015, is that causal, that is, non-spurious correlations are stable across environments. Let's revisit the cow example. Here, background features do not generalize across environments, Switzerland versus Corsica, etc., because the typical background is different in Switzerland than in Corsica. Features of the cows themselves, however, such as the shape of their horns, noses, ears, etc., are the same regardless of where the cow is situated. So those features generalize across environments. In order to enforce invariance across environments, Arjovsky et al. Have proposed invariant risk minimization, IRM, a generalization of the standard expected risk minimization framework, which I will refer to as ERM. And here, ERM, expected risk minimization, is really just a fancy word for the standard loss that typical machine learning training algorithms, such as neural networks, strive to minimize. But whereas in ERM, expected risk minimization, there is no notion of environments, IRM, invariant risk minimization, assumes that the data is partitioned into several disjoint environments. In the example on this slide, there are two environments, A and B. And the task is to train a classification model, for example, to distinguish cow images from no cow images. In the IRM framework, one classification model is associated with each environment, but the models are not independent. Rather, each model is decomposed into two stages, a feature extractor phi that operates on the raw data, and a classifier WA, WB, etc., that operates on the extracted features. The same feature extractor phi is shared by all environments, and the models are tied together by an objective function that stipulates that the optimal classifier, one per environment, should be identical across all the environments. So in a nutshell, the goal is to find a feature extractor phi such that all the optimal environment-specific classifiers become identical. It turns out that this is quite a hard optimization problem though. So follow-up work has investigated how to perform the optimization efficiently. In particular, IRM games is an algorithm that results from considering the optimization problem as a game between the environments. And the task now becomes finding a Nash equilibrium for this game, which can be shown to recover the optimal phi and W. To approximate the Nash equilibrium of this game, each environment performs gradient descent steps on its own environment-specific classifier, and all the environments also update the shared feature extractor phi. After each batch of training, the environment-specific classifiers are then averaged in order to obtain the global classifier W. Zooming out, I'd like to point out that the notion of invariance across environments strikes a nice balance between the most common paradigms for spurious correlation removal, bias mitigation and causal inference. On the one hand, unlike causal inference, approaches based on invariance across environment do not require specifying a causal model. On the other hand, unlike bias mitigation, we need not specify each and every bias. Rather, the focus shifts to choosing a partitioning of the data into disjoint environments. Let me put together the concepts we've covered so far. Invariance across environments, IAE, is a high-level notion, a way of characterizing causality via invariance. IRM is one level down in the implementation stack. It provides an objective function that operationalizes invariance across environments. IRM games, finally, is even further down on the implementation stack. It provides an efficient way of performing the optimization specified by IRM. Let's look at IRM games in action on a language modeling task. In the forward pass, we encode text using phi, the feature extractor. We pass it through each classifier and then build the average to obtain the global classifier. On the backward pass, if the data point is from environment A, then we update the model via backpropagation WA, the environment-specific classifier part, and phi, the global feature extractor. If, however, the data point is from environment B, then we update only WB, the classifier specific to environment B, and also again the global feature extractor phi. So you see that the feature extractor phi is always updated regardless from which environment a data point is coming, whereas the classifier WA, WB, etc. is updated only for the respective environment. This was the theory, so let's see if it works in practice. A disclaimer, this is work in progress, so what I'll show you is just a glimpse at some early results. Our goal is to see if training a language model with IRM rather than with the standard ERM results in fewer spurious correlations. In order to have a clean setup where we can study this question, we carefully craft a set of environments with minimal and controlled changes such that we can actually tell whether spurious correlation was removed or not. As a concrete example, we will use gender bias. It is well known that in naturally occurring text, many words such as profession names, doctor, nurse, bricklayer, etc., are statistically associated with certain genders. So there's a correlation between those words, the profession names in the example I gave, and with gender words. So, for example, pronouns such as he, she, etc. In order to make sure that these are spurious correlations, we also synthesize an artificial environment where all gender terms are inverted. For example, he becomes she becomes he, etc. Specifically, we split the original data into two environments with proportion p versus 1 minus p. A fraction p of the original corpus is completely left unchanged, nothing done there. The remaining portion, 1 minus p, is modified such that we simply invert all gender terms. For example, whenever we see he, we change it to she. Whenever we see she, we change it to he, and so on. So we refer to these two environments A. A is the unchanged one, B is the changed one. As a result, the environments A and B come from essentially the same distribution, the only difference being the correlations of words with gender words. In our evaluation, we will then consider two setups, a balanced and an unbalanced setup. The intuition here is that in the balanced setup, both IRM and ERM should successfully remove gender correlation. Why is that? Well, because since in environment B, the gender terms are flipped, basically any correlation, any spurious correlation bias that we have originally in environment B is canceled out by flipping the bias in environment B. That's in the balanced setup. In the unbalanced setup, however, we have 4 times as much from the original corpus as from the flipped portion. So that means there is still a preponderance of the original bias, and it's only slightly turned around to a certain extent in the flipped portion. The flipped portion is overridden. So here we would expect ERM to fail because the bias is effectively still there, whereas IRM should, in the ideal case, that we would hope, work because it can separate those two environments from each other, A and B. To train the language model, we start from a pre-trained model. That model was pre-trained via standard neural network training, that is via ERM, and then we fine-tune it via IRM. If a model successfully removes, if a model successfully removes the spurious correlation with gender terms, then whenever at test time the model is asked to predict a masked word whose ground truth is a gendered pronoun, then the model should give an equal probability to the male and to the female version of that pronoun. Technically, the entropy over the gendered variance should be large. So let's look at the results. First, we consider the balanced scenario. Here, the dashed line is the entropy of the gender variance before IRM-based fine-tuning. So we see that in the balanced setting, both ERM and IRM have an entropy higher than the dashed pre-fine-tuning baseline. So by fine-tuning, both ERM and IRM remove some bias, but IRM in blue does so even more. Next, the unbalanced setup. As you can see, the effect is much stronger in the unbalanced setting on the right. Here, IRM's entropy increases by an even larger margin over the pre-fine-tuning baseline as compared to ERM. The gap between blue and red is larger on the right than on the left. So to summarize, IRM provides an effective way of making language models more robust to biases and thus generalize better. So let me conclude. Typical language is constrained by causal relationships in the world. To model language properly, one might think we would first have to model all those causal relationships in the world. That would be really hard. What are even the variables that such a causal model would have to include? It's unclear. IRM, invariant risk minimization, offers some of the robustness that we could hope to achieve via proper causal modeling without having to specify the causal model explicitly. Therefore, we consider IRM a well-suited paradigm for language modeling. Here I showed you a first glimpse. I'm looking forward to continuing our investigations together with the Microsoft Turing team and to share more results with you in the future. So thanks for your attention. If you have any questions or comments, I would be happy to receive them via email. Thanks a lot.